Hello, dear viewers. I am Dr. Shikha. I am working as assistant professor at ABES Engineering College, Ghaziabad in the Department of Applied Science and Humanities. Today, I am going to deliver a lecture on molecular orbital theory. First, I will discuss some important point of the molecular orbital theory. Molecular orbital theory was given by Hund and Millikan. First point of molecular orbital theory is that molecular orbitals are formed by the combination of the atomic orbital, and in this process atomic orbital completely lose their individual identity because they convert into the new molecular orbital. Second point, only those atomic orbital which have same energy and symmetry can combine to form molecular orbital. Same energy means 1s orbital can combine only with the 1s orbital. A 1s orbital cannot combine to the 2s orbital, and 1s orbital cannot combine to the 3s orbital due to the difference in their energy. Same symmetry means their symmetry should be same. Suppose if we want to combine s orbital with p orbital, as we know by default that pz orbital exists on the internuclear axis. So s orbital can combine to the pz orbital, not to the px and py orbital. Two types of molecular orbital are formed, in which one would have bonding molecular orbital and another would be the anti-bonding molecular orbital. And atomic orbitals are represented by the SPDF, whereas molecular orbitals are represented by sigma, pi and delta orbitals. Molecular orbitals are polycentric and atomic orbitals are monocentric. Why molecular orbitals are polycentric? Because molecular orbitals are formed by the combination of the molecules. Therefore, there exists more than one nucleus. Therefore, they are said to be the polycentric. Next point, like atomic orbital, electrons are filled in the molecular orbital in the increasing order of the energy. Increasing order of the energy means first lower energy orbital will fill, then higher energy means first 1s orbital will fill, after this 2s orbital will fill, then 2p orbital will fill, so on. Next point, number of the molecular orbital form is equal to the number of atomic orbital take part in the bond formation. Suppose we have two atoms, 1s of is A atom and 1s of the B atom. So these two atomic orbital when will combine, they will form two new molecular orbitals, in which one will be the bonding molecular orbital and the another will be the anti-bonding molecular orbital. Next point, the energy level of bonding molecular orbital is less than the individual atomic orbital. Suppose these two are atomic orbitals, it is the energy level of these two atomic orbitals. So when the molecular orbitals are formed, the energy level of bonding molecular orbital is less than that of the anti-bonding molecular orbital. Why this is happening? This is happening because the electron density in case of the bonding molecular orbital, it exists between the two nucleus, and due to this the internuclear attraction increase between the electron and the nucleus. Therefore, due to the attraction, the energy of the molecular orbital will be less. Therefore, it exists on the lower side of the molecular orbital. However, in case of the anti-bonding molecular orbital, here the electron density is present on the side of the nucleus. So, due to this, the nucleus come closer and they cause the internuclear repulsion, and due to this repulsion the energy of the anti-bonding molecular orbital is increased. Therefore these molecular orbitals are destabilized. Next point, the electrons are filled in the molecular orbital according to the following order. So Up to nitrogens means up to 14 electron. Here the electronic configuration would be 1 sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, then pi 2px equal to pi 2py because both have the same energy. And then sigma 2pz and then pi star 2px, pi star 2py, and after that sigma 2pz. However, in case of the oxygen, or the atomic number more than 14 molecules, here the difference exists from the 2pz orbital. Here after the sigma 2px orbital, first sigma 2pz orbital will come and then pi 2px and pi 2p will come. Why this is happening? Actually, if we see from hydrogen to nitrogen, size of these atoms are small, and due to the small size, when 2s orbitals is filled, after that if sigma pz orbital is going to fill, then there is the repulsion between the sigma pz and sigma 2s orbital, due to which sigma pz orbital flip from the lower position to the higher position, as I am showing it this in this diagram. So it flip from the lower state to the higher state due to the repulsion between the sigma 2s orbital and sigma 2pz orbital. Whereas in case of the oxygen, as the size is comparatively bigger than the earlier atom, therefore there is no repulsion between the sigma 2s and sigma pz orbital. Therefore it exists earlier from the pi 2px and pi 2p orbital. Next point, molecules or ion with one or more than one unpaired electrons are paramagnetic, where the molecular orbital with all the electrons are paired are called diamagnetic. Next point, the stability and strength of a chemical bond is expressed in terms of the bond order. As we know very well, the higher is the bond order, higher is the stability of a molecule, or higher is the strength of the molecule. So, bond order is calculated from this formula, which is half of the difference between the number of the electron present in bonding molecular orbital minus number of the electron present in the antibonding orbital, where A represent the antibonding molecular orbital and B represent the bonding molecular orbital. Now, we will discuss some homonuclear diatomic molecules. So first, homonuclear diatomic molecules are those molecules which are formed from the same atom. Examples are like nitrogen, oxygen, hydrogen, boron. So first we will discuss nitrogen. The electronic configuration of the nitrogen, as we have discussed, it will be the sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Then after the 2s, 2 pi x and 2 pi py will fill. After that sigma 2pz will fill. So now we will see how the electron will fill in the bonding molecular orbital. As we know, the atomic configuration of the nitrogen is 7. So it have 1s2, 2s2 and 2p3 electronic configuration. So these two atoms will combine and form new molecular orbitals. So now we will see how the filling of the electron take place. One s of one nitrogen atom will combine with the 1s of the another nitrogen atom, and it will form these two atomic orbital will combine and form two new molecular orbital, in which one will be the bonding molecular orbital and another will be the antibonding molecular orbital. In the similar way, 2s orbital will combine. Two 2s orbital are going to combine. They will form two new molecular orbital, in which one would have the sigma 2s bonding molecular orbital and sigma star 2s bonding molecular orbital. Now, the 3p orbital will combine and they will generate 6 new molecular orbital, in which 2 will be the pi 2px and pi 2py and 1 will be the sigma 2pz. Then the filling of the electron will take place in the pi 2px, pi 2py and sigma star 2pz. So after the filling of this electron, the electron will fill as here 6 electron is present. So first 1 electron will come from this orbital to here, and then 1 electron will come from the this orbital to here. So then the next electron will fill next electron will fill and pairing will take place after the filling of this pi orbital. Then the remaining electron will enter into the sigma 2pz orbital. So from here we can analyze the magnetic behavior of the nitrogen molecule. As from the figure, it is clear that all the electrons are paired in the molecular orbital. Therefore, the nitrogen molecule exhibits the diamagnetic behavior. Also, the bond order we can calculate from the formula 1 by 2 electron in bonding. So, bonding first we will calculate 2 electron is present in sigma 1s, then 2 electron is present in sigma 2s, then pi 2px, pi 2py and sigma 2pz. So, here total electrons are 10. Now we will calculate the electrons present in the antibonding molecular orbital. 2 electrons is present in sigma 1s and 2 electrons is present in the sigma star 2s. Therefore, total electron are 4. So, the bond order of the nitrogen molecule will be 3. Now we will discuss nitrogen cation. It have 13 electrons. So pairing will be similar as to the nitrogen molecule. 1s and 1s atomic orbital will combine and it will generate 2 new molecular orbital. Then 2s and 2s orbital again will combine. It will again generate 2 new molecular orbital, and then 2p and 2p will combine and which will generate 6 new orbital. As we know that as orbital are completely filled, so all the 4 electron will paired up in 1s orbital. Similarly, 2s orbitals also the electrons are completely filled. Therefore, the 4 electron will enter in the bonding orbital and anti-bonding molecular orbital. However, as we can see, the 3p orbital are 3 electrons present in the one nitrogen atom and 2 electrons are present in the another nitrogen atom. Therefore, first the one electron will enter, then the pairing will take place. After the pairing, the remaining electron will go in the sigma 2pz. And from the diagram, we can say the nitrogen cation is showing the paramagnetic behavior and its bond order is 2.5. Now, nitrogen anion, it contains 15 electrons. Similar to the nitrogen cation or nitrogen, here also the electron will fill in the same manner. First electron will enter in the 1s orbital and form antibonding and bonding molecular orbital. Then the remaining electron will enter in this 2s orbital and they will form sigma 2s and sigma 2 star. After that, one p orbital of nitrogen atom contain 3 electrons and the remaining contain 4 electrons. So first pairing of the 2p orbital will take place. After that, remaining electron will the sigma pz, and after that one more electron is there. So it will go in the anti-bonding molecular of the pi 2px. So from the figure, we can say the molecule exhibit the paramagnetic behavior, and if we calculate its bond order, so electrons present in bonding molecular orbitals are 10, whereas electron present in anti-bonding orbitals are 2, 2 and 1. So 5 electrons are present in anti-bonding, therefore it will show the it will show the bond order 2.5. Now if we discuss stability, as we know very well that bond order is directly proportional to the stability of the bond stability of the molecule. So we have calculated that the bond order of the nitrogen is 3 and nitrogen positive and nitrogen anion have bond order 2.5 and 2.5. Therefore, the stability of the nitrogen will be greater than comparison to the nitrogen cation or nitrogen anion. Also, the nitrogen cation and anion have same bond order 2.5. Therefore, they will show the similar stability. We know the bond order is inversely proportional to the bond length. Therefore, the bond length of the nitrogen cation or anion will be greater than comparison to the nitrogen atom. Now we will discuss the oxygen molecule. Oxygen molecule contains 16 electrons, and here the difference will be only in the 2p orbital. So here first sigma 2pz orbital will be filled. After that, remaining pi 2px and pi 2p orbital will be filled. So we know the electronic configuration of oxygen. One oxygen atom is 1s2, 2s2 and 2p4. So first electron will fill in the 1s orbital and they will form two new molecular orbital, in which one is bonding molecular orbital and another is anti-bonding molecular orbital. Similarly, 2s orbital will combine and they will generate two new molecular orbital, in which one is sigma 2s and sigma star 2s. Now the 2p orbital, 3 orbital will combine and it will generate 6 new p orbital, in which 3 are the bonding molecular orbital and remaining 3 are the anti-bonding molecular orbital. So first pz orbital, one electron will combine from this atom to this atom and it will paired up. After that, pi 2px orbital will pair up. After the pairing of these electrons, then the remaining electrons will goes to the anti-bonding orbital of the pi x and pi py. So due to the presence of unpaired electron, the oxygen molecule also show the paramagnetic behavior. And if we calculate its bond order is 2. Due to the presence of bonding electrons are 10 and anti-bonding electrons are 6. Then superoxide, it contains 17 electron. 17 electron will also fill according to the parent molecule, oxygen molecule. First electron will fill in the 1s orbital, then in 2s orbital, and then in the 2p orbital. So here one oxygen atom contain 4 electron and the another oxygen atom contain 5 electrons. So after filling of the 6 electron, 7th electron, 8th electron and the remaining 9 electron will come in the anti-bonding orbital, because pairing of the energy and electron will take place. Now from the figure we can clearly analyze its paramagnetic behavior, and if we calculate its bond order, it show the bond order 1.5, means it show the fractional bond order. Then peroxide, it contains 18 electron. First electron will fill in the 1s orbital, then in 2s orbital and then 2p orbital. Due to the presence of 18 electron, the p orbital contain 5 electrons, and now the electron first will fill sigma 2pz, then pi 2px and pi 2py. After that, anti-bonding of pi x and pi py. So after the filling of the 6 electrons, 7th electron will enter sigma as 8th electron, then 9th electron and the remaining 10th electron will enter also here in the anti-bonding. So this will show peroxide of oxygen will show the diamagnetic behavior, and the bond order of the molecule will be 10 minus 8, means it will show the bond order 1. Since the bond order is directly proportional to the stability of the molecule, therefore the order of the stability of the oxygen molecule will be oxygen would have greater than superoxide and superoxide would have greater than peroxide. And the inverse relation will be the between the bond order and bond length. So bond length will be greater of the peroxide form than superoxide form and then oxygen molecule. That's all from my side. Thank you.